we are going to see about unimolecular nucleophilic substitution reaction, that is SN1 reaction. In our previous video, we saw SN2, that is bimolecular nucleophilic substitution reaction, in which the reaction takes place in a single step and the transition state must not be crowded for the high rate of the reaction. See this, that is the reaction will proceed very fast with in the case of primary, okay, because it is less crowded, the transition state is readily formed. So according to that concept, if we think, we will see that when the reaction is taking place with a tertiary carbon, the relative reactivity will be very slow. But see what happens, see this reaction, tertiary butyl bromide, it even reacts with a weak nucleophile. So that is OH minus ion is a strong nucleophile where the reaction will take place via SN2 mechanism. But here it's a poor nucleophile, and see this tertiary butyl bromide is sterically hindered. Okay. And it forms the product tertiary butyl alcohol where bromine is replaced by OH minus ions. Okay. And here we consider that this reaction almost will not take place according to SN2 mechanism because the rate becomes very slow. But see what happens, but in fact see the fact, it is over 1 million times faster than the reaction of methyl bromide, that is a compound with no steric hindrance with water. Okay, so see this one is having more steric hindrance, but it is very fast, the reaction takes place in a very fast manner. So what we come to understand here, the reaction must be taking place via a different mechanism, that is here we are going to see about SN1, that is the different mechanism SN1. And see here in this case particularly tertiary carbons, so crowded carbons will take place, undergo a substitution reaction via SN1 mechanism. Now we'll move to the reaction mechanism. Before studying the mechanism, we must understand the kinetics of the reaction. Okay, the kinetics of the reaction, if you see the rate of the reaction depends on the concentration of the alkyl halide alone. So what is the meaning is, if you are doubling the concentration of alkyl halide, then the rate of the reaction also doubles. And if you change the concentration of the nucleophile, they found out that there is no effect on the rate of the reaction. So what is the point is, the rate of the nucleophilic substitution reaction, that is here this reaction, the rate will not depend, only depends on the concentration of the alkyl halide and not on the concentration of the nucleophile. So what is the meaning? The reaction is first order reaction and you can see the rate is proportional only to the concentration of the alkyl halide, and so we are saying this as unimolecular nucleophilic substitution reaction, that is SN1. Here 1 stands for unimolecular, N stands for nucleophilic and S stands for substitution reaction. Okay. Now we can understand the mechanism. After studying the kinetics, we have found that the reaction rate depends only on the concentration of the alkyl halide. So what is the meaning here? What is the reaction? The rate determining step involves only the alkyl halide. That is the point. Okay, so according to that point, we can study the mechanism of the reaction. You see the mechanism. First step, here the reaction takes place in 2 steps. Okay, and the first step being the slow step is the rate determining step. And what is the first step? It is the ionization of the alkyl bromide, that is carbon bromine bond breaks heterolytically. A heterolytic cleavage takes place, and so what happens, that bromide ion is removed as Br minus ion and we are getting a carbocation, that is tertiary carbocation, which is highly stable. Yes, tertiary carbocation. And now this is the first step and this is the slow step and this is the rate determining step, and that step is ionization. And what happens in the second step, now the nucleophile. Okay, here so that we can use a very weak nucleophile because the rate of the reaction will not depend on the concentration of the nucleophile. So even a weak nucleophile can undergo reaction. So what happens? Water molecule being a neutral nucleophile, it attacks the carbocation, and see the reaction mechanism. It that oxygen carries a positive charge, and we are getting OH2 with the oxygen with a positive charge, and in the next step, that is the fast step, this one H is again one water molecule comes, and this it removes that H plus, and so that what is the product formed is alcohol, tertiary alcohol. So the first step is ionization, second step is the attack of the nucleophile, and the last one, that is the proton transfer to form the final product, tertiary alcohol. So here the reaction takes place in two steps, main point, and the reaction involves the formation of an intermediate called carbocation intermediate. And so what happens to the hybridization? You see, hybridization, you are starting with sp3 hybridization. The carbon is tetrahedral in shape, and that is the tertiary butyl bromide is tetrahedral, and now the reaction takes place, and you have what is formed? Carbocation is formed, which is the trigonal planar in shape, and that is this tertiary carbocation, you know, it is more stable than that of secondary and that of primary. So when a reaction is taking place via primary, if a primary substrate is present, the reaction continues via SN2 mechanism. If the reaction contains a tertiary carbon, then the reaction nucleophilic substitution follows SN1 mechanism. This is obvious from this. Now we'll move to the next point. What happens to the reaction coordinate diagram? See the reaction coordinate diagram. You can see the rate determining step, the reaction, since the reaction takes place in two steps, you can see two humps. Okay, the first step being the slow step, that is the rate determining step, and in the intermediate well that is formed in that is a well formed in the hump. Okay, and that well corresponds to the formation of carbocation intermediate, that is R plus, and then the nucleophile attacks at this position, and then you are getting a product. Okay, that is ROH, that is protonated, and then removing that proton, you are getting the final product. And so we can see the reaction coordinate diagram. The energy increases here, and the first step is the slow step. So this is the reaction coordinate diagram for SN1 reaction. Now we'll move to the next one. Comparing to the relative rates, you know, tertiary, because see the rates, see you can see how we cannot even imagine. See the rate of the reaction, the same SN1 reaction when the reaction is takes place with the primary, that is methyl bromide. See the reaction, it is considered as 1, and it is ethyl bromide, again it is 1, but in the secondary the rate has increased relatively, that is 11.6 the rate. But see with the tertiary, it is nearly 122, that is very high, that is nearly 12 lakhs times, it is more, that is, so we are that only saying million times it is. Okay, so what is the point here? The tertiary carbocation is more stable and is therefore easier, very easier to form than a secondary carbocation, which in turn is more stable and easier to form than a primary carbocation. Like that, tertiary alkyl halides are always more reactive than secondary alkyl. That is also another important point. And so here the SN1 reaction, always a tertiary compound will follow this one. Okay, if it is a primary alkyl halide, that will not undergo SN1 reaction. See, that is another important point you have to remember. The primary alkyl halides and methyl halides cannot undergo SN1 reaction at all. They will, if they are present, they will immediately follow SN2 mechanism only. Okay, so the relative rates also, you can see the comparison, that is tertiary is more reactive, then comes the secondary, and then the least reactive is primary alkyl halide. Okay, next point. Now coming to the stereochemistry, that is also very important. Okay, so here since the reaction takes place in two steps, first step is the formation of a carbocation where there is change in hybridization. In this case, the first sp3 hybridized carbon is converted to sp2. So sp2, the shape is trigonal planar. If it is trigonal planar, what can happen? This carbon being positive, this carbon can be attacked either by above or back side, that is front side attack or the rear side attack, back side attack, both are possible. So what happens to the product? If you are starting with if always you will be getting both the inversion of configuration and retention of configuration, or configuration, the same configuration. The leaving group will be that is the nucleophile will attach the position at which the leaving group is present or to the opposite. Both are present. So you are getting, usually you will get a mixture. If it is an optical isomer, then we will be getting racemic mixture, usually racemic mixture, or almost not purely racemic mixture, some with the inversion of configuration. But product stereo, if you are studying the stereochemistry, you must remember, if a reaction follows SN1 mechanism, you will be getting both inversion of configuration and retention of configuration. Both products are possible, but almost 10% inversion of configuration will be high. For this, there must be a reason behind this. Yes, see this one, when if it is an first the starting with the plus isomer, you are getting plus and minus isomers. This is the product. Okay, in the case of SN1. So if you are getting more amount of inversion of configuration, see this is also the same thing. The inversion of configuration, I have given on some example. If you are starting with the minus compound, that is S compound, sorry, it is S sinister compound, and the product is both R and S. That is one with inversion of configuration and another with retention of configuration. But when we are observing it, almost 50 to 70% will be inversion of configuration and the rest will be only retention of configuration. So what is that? So here it is not pure racemization. Complete racemization is not taking place, only partial racemization. So what is the reason behind the partial racemization? That is a simple point. So you can understand, that was given by the scientist Saul Winston. Okay, he explained that when that molecule is being dissociated, it forms an intimate ion pair. You can see this intimate ion pair. Now, if the intimate ion pair is very closer, then what happens is only from the backside attack the nucleophile can enter. So you will be getting more amount of inversion product. But if they are separated by a solvent, so it may get separated and if they move apart, so that you can get, that is it can attack the position of the leaving group. So what happens, see this, you can understand in a clear way. Bromine has diffused away, giving water to equal access. So in this case, you will be getting both retention as well as inversion equally. But when they are forming an intimate ion pair, when bromine has not diffused away, so it blocks the approach of water to one side of the carbocation, and so what happens is inversion of configuration becomes somewhat higher. So only here we are seeing that it is partial racemization. Okay, so these are the main points about SN1 mechanism. While considering SN1 mechanism, we will be seeing one more point, that is, it is carbocation rearrangement. So in almost majority of the cases, in the case of SN1 reaction, the expected product will not be the actual product. What would have happened is, there may be rearrangements. Okay, so when a reaction forms a carbocation intermediate, always check the possibility of a carbocation rearrangement. That is also very important in the case of SN1. So in SN1 reaction, you will almost majority cases you will be not getting the expected product. Okay, it will be a different one. Okay, so because rearrangement takes place, always the carbocation that is formed will move towards the stability. So if it is a secondary carbocation formed and there is a possibility for converting that into a tertiary carbocation, then it will convert it to a tertiary carbocation, and so that the position of the nucleophile will differ. Okay, now you can see an example. See this example. I have taken this compound here. What is this? If the reaction takes place via SN2 using a strong nucleophile, then what will happen is this Br minus ion is removed and you are getting a product where bromine is itself present, OH group is present. Okay, the leaving group, the same position, the nucleophile is present, entering group is present. But when you see the SN1 mechanism, here the weak nucleophile we are taking, so what happens? First you will be preparing a secondary first what is formed is secondary carbocation, and in the second step what is here, secondary carbocation is formed. But there is a possibility for this secondary carbocation to convert to a tertiary. See this, what happens, this methyl, here what happens is this H carbon attached to this carbon, this H is removed as H minus ion, that is hydride ion, and this will move from the first carbon to the second carbon. So it is called as 1,2 hydride shift, and this was given by the scientist Whitmore, and it is also called as Whitmore shift. So it is 1,2 hydride shift. So what happens? This hydrogen moves to this position, forming a tertiary carbocation, and now the nucleophile will attack that carbon, giving a different product. See, this one is formed and you are getting 2-methyl-2-butanol. So if you are starting with the 2-methyl-3-2-bromo 3-methyl-butane, according to SN2 mechanism you will be getting 3-methyl-2-butanol, and according to SN1 mechanism the product will be 2-methyl-2-butanol. That's very important. Okay, I have dealt with one more example. See this example. Here there is a different shift. Instead of hydride shift, you are seeing a methyl shift. So you can see methyl shift. Here also the compound 3-bromo 2,2 dimethyl butane, and if it undergoes SN2, here the place of bromine, this OH minus ion is present. But in the case of SN1, see what happens. Here there you are getting a secondary carbocation, and now what happens? This methyl group shifts as carbanion. So this shift is called as 1,2 methyl carbanion shift, or simply you can say it as methyl shift. And so what happens? The secondary carbocation rearranges to form the more stable tertiary carbocation, so that what happens, that well will go deeper the well, the reaction will take place in a very fast manner. Okay, so that is all. That is important in the way you are considering the coordinate diagram, reaction coordinate diagram. And now coming to this, what with this water will attack this position, and so we'll be getting this one protonated compound, and then finally with water H plus is removed, and so you are getting the final product. So see the product here, 3-bromo 2,2 dimethyl butane will lead to 3,3 dimethyl 2-butanol in the case of SN2, but in the case of SN1 that is not the product. Instead it is 2,3 dimethyl 2-butanol. So these are the interesting facts about SN1 mechanism, and so you have to remember all these things while studying SN1 reaction. Okay, that's all the points. Thank you.